right, so last time we were talking about implicit differentiation, and I pointed out there's some really dangerous issues here. We might inadvertently make a reference to a derivative of a thing that you're not allowed to take the derivative of, namely something that's not a function. Right? It's a very serious problem. Again, it's very important if you're going to do mathematical reasoning that it all has to be meaningful statements, right? So anyway, how do we avoid this problem? We made the observation last time that if you do have what I'm going to call a problem, when you have a curve in the xy plane described as a level set, if you have a problem, right, that's because the curve is wrapping under itself, which means that curve must be momentarily vertical, which means that its gradient, the gradient of the function whose level set we're looking at must be horizontal, which means, just looking at what the components of that gradient are, it means that the y component of that capital F function must be 0. So what we have altogether then is that when there's a problem, the y partial will be 0. Or said differently, if the y partial is not 0, then there is no problem. Okay, so this is where we ended it last time, and I want to point out that the same reasoning, morally, applies when you have more variables. If you have a surface in space, described as a level set of a function of 3 variables, right? So some equation involving x, y, and z describing some surface. And I asked the question rhetorically here, if you have some point, let's say there, and if I ask, locally, can I view, let's say, z, near that point, can I view z as being a function of x and y? Well, for this point here, there's no problem. Yeah, sure, go ahead. I mean, it's just a little piece of surface and passes the vertical line test, no issue. At that point, right? But if we were to entertain a bad point, such as this one, there's going to be a problem. And again, what is it that manifests the problem? The problem is that the surface at that point is in the process of wrapping under itself, which could only happen, I've already forgotten what colors I used previously, could only happen if you have a vertical tangent plane. The surface must be, if it's in the process of wrapping under itself, the surface's tangent plane would just have to be vertical there. Anyway. The surface itself would have to be kind of going vertical. Which means that we would have a horizontal gradient, because, of course, gradients are always perpendicular to level sets. And if there is a horizontal gradient, and I forgot to highlight the vertical tangent plane, then we must have that the z partial, the vertical component of that gradient must be 0 if that gradient is horizontal. So, very, very similar argument, and now I'm going to point out that this generalizes even more. And here's the statement of the theorem. Basically, if you're looking at a level set of a function, right, and if you're interested in the possibility of whether you can locally view one of the variables as a function of the others, then the test is that partial is not 0. And notice the pattern we already kind of saw happening here. Let's see here, and let me clean up for emphasis purposes. You want to know whether y is locally a function. It's arbitrated by what the value of the y partial is. Here, we wanted to know if z was a function, arbitrated by the z partial. So the general rule, always, if you're trying to decide if one of the variables can be viewed as a function of the others, take the partial with respect to the variable that you want to view as a function. Nice, simple, little pithy little rule, and of course, make sure that it's not 0. Okay, so example. Here is a surface in space, and let the record show I don't have the slightest idea what this looks like. right? And I don't want to have to figure it out. I see a couple of cubes in there, and this is going to be oh my gosh. There's no rotational symmetries. This doesn't look like an easy deformation of anything I've already seen before. I am scared of this surface. I don't know, right? And yet, maybe I might be interested in studying this surface, near some particular point, and I would like to know if I'm looking just near that particular point on this mystery surface, can I view X locally as being a function? Near that point, forget about I don't know about other, way farther away elsewhere on the surface, I don't care. But near that point, can I view X as being a function of the other variables, of course? Well, so following the rule, whichever variable you want to view as a function, take the partial with respect to that variable. Specifically, what do I take the partial of? I take the partial of, the function whose level set I'm looking at. That would be this function here. That's the function whose level set I'm looking at. Is everybody with me? I see I'm just following the pattern from the previous page. And okay, so compute. That partial is this. I'm interested in what's happening at this point here, so I'm going to plug in, at that point 1, 2, 3. At which point this becomes 4, which, as required by the theorem, not 0, so no problem. Yes.
Does it matter if the level set is f equals 0?
It does not. It does not. Yeah. So if you wanted, you'd be perfectly welcome to take, what we've got here, and how about this? So I could take this 27 and move it over to the other side, right? And then the thing that I'm taking the partial of now doesn't have that 27 in it. And how does that affect the partial derivative? Well, not at all. Yeah. So it doesn't matter what the constant on the right is. You can move constants on either side, but it does have to be a level set. That is very, very important, of course. That's central to the argument. So as long as what you have on the other side there is a constant, no problem. Good stuff. All right. So now, good news. We know how to tell, at least in most cases, when one of the variables is a function of the others. Now, why did I want to know if one of the variables is a function of the others? Because I wanted to take a derivative of it, right? I was scared to death that I might accidentally take a derivative of something that isn't a function, which of course is garbage, right? So now that I know it's a function, now I'm allowed to take derivatives of it. And how do we do that? So there's a couple of points of view you can take on this. Here's the first point of view. I'm not going to go through this. This is what I'm going to call appropriate and complete, at least to the level of rigor that's appropriate to this class. And also there's a lot going on here that ends up not really mattering. And furthermore, this is a pretty scary looking picture, and it's just more than we need to discuss. So what I'm going to do, I'm going to go through this much simpler version. It's morally equivalent to the above. It's a lot easier to look at. Now, I'm going to start right off with a confession that this violates one of my big rules. You may recall one of my big rules. If you're going to apply the chain rule, you need to have a composition of functions. What comes out of the one function needs to be what goes in to the next function. And if it's not, then I don't know what you're talking about, and that's not a chain rule. The chain rule is only about composing functions. So what am I doing here with... there it is. What am I doing here with this diagram, which clearly does not satisfy that rule? And all I'm going to say about that is that really, if you get right down to it, this is just a compact representation of what I have over here, which does satisfy the rule, and to which the chain rule definitely applies. And I'm going to sweep it under the rug how these are morally equivalent diagrams, and just ask you to trust me that if we focus our attention on this suspicious looking simplified diagram, everything's going to be fine, and we're not going to run into any problems, and it's all good. And I'm just going to hope you'll be willing to trust me on that. So, okay, so here's the idea. Keep in mind, f is a function of a bunch of different variables, and I set f equal to a constant, and by virtue of setting it equal to a constant, I know that when I start moving one of the variables, well, wait a minute, hey, if I start moving one of the inputs to f, that's going to make f change, but f is not allowed to change, and the way we're going to make that right is by also then correspondingly changing this other variable. So if xi, when I say that xi is a function of xj, what we mean is that when this changes in such a way as to preserve the requirement that f remain constant. So xi moves in exactly whatever way is necessary to counter the effect of xj changing. That's the big idea. Okay. So, let me write that down. When xj changes, that makes a direct contribution to f changing. Furthermore, when xj changes, that causes xi to change, and xi changing also makes a contribution to f changing, and that gives us the product of these two factors. So roughly speaking, again, we have kind of two paths. Changes in xj can propagate to changes in f. Altogether, of course, have to add up to 0 because f doesn't change total, right? And so these two paths contribute these two terms to a calculation whose answer has to be 0. Is everybody with me? All right, and now we just have to recall, oh, wait a minute, what was I trying to compute here? I was trying to compute the partial of xi with respect to xj, right? I've got this newfound ability to view xi as being a function of xj. Its partial with respect to one of the other variables is what I want to know. So you just solve for it, and you get this formula right here. All right, now a few things to say about this formula. Good news, bad news. The good news is that forgive me for my sins here, but it kind of looks like that cancels with that, and then the denominator of my denominator is my numerator, and it kind of looks like it's giving us, in fact, exactly what it's supposed to, right? There's a lot of sort of, bogus algebra of fractions that seems to almost perfectly align to give us the thing that we want to compute, and that's nice I'm going to call it a memory tool. But the big bad news, of course, is that there's this minus sign here, and that minus sign is extremely important. That is part of the answer. Why is that minus sign here? The minus sign is there because I'm looking at a sum of two things being 0. Morally, it comes from the fact that these two terms have to be opposites of each other to add up to 0. Their being opposites of each other is why you have a minus sign there. And of course, it's very important that they be opposites, not equals. And again, so you can kind of see this same sort of bogus algebra here. If I were to pretend that this and that cancel, then it kind of makes it look like this is the same as this, which of course it's not. They're opposites of each other. These are not fractions. This algebra of fractions is all nonsense. Right? But as a memory tool, I think it's kind of nice. But just make extra sure that you don't forget this minus sign. That minus sign is huge for two reasons. First of all, your work is wrong without it. That nice simple pitch. Let's start with the easy point, right? But worse than that, give me a second. Worse than the fact that your answer is wrong it's not an innocent sign error. Let me explain what I mean by that. We've all made innocent sign errors. I do it all the time. It's embarrassing. 3 minus signs, and I'm trying to do too much algebra too fast, and somehow 3 minus signs, and I accidentally cancel all of them. Right? I mean, it's just, it's a triviality. It's happens to the best of us. It doesn't really mean much when you have what I'm going to call a trivial sign error. That's not what this is. If you forget this minus sign and write down this equation, where would this come from? I mean, what am I supposed to believe about a student who writes this down? And the problem is, this is exactly what a student would write down if they truly believed that these canceled and that this denominator of my denominator is my numerator. If they actually believe that these are fractions and that the algebra of fractions applies. In other words, without that minus sign, your work looks like that of a student who has a fundamental misunderstanding of the big ideas. So I'm going to throw out that I think that this minus sign here, this very important minus sign, one of the most important minus signs in the class. I don't want to overstate it. It's definitely top 3, though. There's a couple other minus signs that are a big deal, right? We'll get to later. But it's a pretty big one. So please make sure not to forget this minus sign. Does that make sense? I'm making a big deal out of it in the hopes of decreasing the number of students who will oops it. Okay. All right. So let's do an example. Here we go. I'm sorry. You had a question. Yes. Thank you.
Why, when we're in that diagram, why do we not at all look at
the other variables? Yeah. Great question. Thank you. So keep in mind we're talking about a partial derivative. Let's see here. Yeah, partial derivative. When you're taking a partial derivative, all the other variables are to be assumed to be constant. So let's keep in mind what's going on here. Xi is the one that's the function. It's a function of all of the other variables. Colors. All of the other variables, of course, being, these. But because I'm taking a partial derivative means that only xj, only the one I'm taking the partial with respect to, is allowed to change, and all of the other variables, if I can get my stylus to work, all of the other variables have to be constants. And because they're constants, there are no changes propagating through them.
And then how do we know that those two things cancel out?
Yeah, because f is not allowed to change. Remember, f is a constant, right? So this is fixed, and so the grand total change in capital F has to be 0. Yep. Okay, so example. Same surface that we talked about previously. Same exact surface. Same point. 1, 2, 3, near which I want to understand the surface, and specifically where I've already established, I should say, that x is locally a function of the other two variables. Okay, well, if x is locally a function, I am perfectly within my rights. So start talking about its partial derivatives. And let's say partial derivative with respect to z. So z is the variable. That means the other variables, aka just y, are to be treated as a constant. Now let's take a quick pause and recognize all 3 of these variables are now playing different roles. Right? X is a function, y is a constant, and z is the independent variable. So, you gotta make sure you keep track of what's doing what. Per the formula on the previous page, the way I'm going to compute the partial in question is by, first of all, remembering my minus sign, because I'm scared to death I'll forget it. Right? And then next, remembering that it's going to be a ratio of partials of f. And which way does it go? It goes the way that if these things were fractions would make it kind of right, except for the minus sign, which of course it fails to account for. So I put the z partial in the numerator because the denominator of the numerator feels like it ought to be stylus bias should be the denominator. Right? That's just a memory tool. That's it. It doesn't mean it. What I just said is not mathematically valid, right? But it is handy memory trick. Okay. So, having written that down, we've got some easy partials to compute. Nothing to it. The z partial is that. The x partial is that. Again, can't emphasize enough. Don't forget your minus sign. It's easy to kind of oops it. Right? And you plug in the value where you're computing and answer. Anybody with me? Very last comment I'm going to make, and then we're going to go on to chapter 3. Most of the time, in a question that involves implicit differentiation, you do not already know that the thing you want to take a partial of is actually a function. That is a weird feature of this example. And the reason that weird feature is in here, it's just straight up given that x is a function. Why is that given? Well, because we already addressed that previously. We've already asked and answered that question. Right? So I thought it would be sort of unnecessary waste of pencil lead to write that over again. Right? So that's, let's say it this way, these two examples that I've just gone through think of them as part A and part B of a single example. So when y'all see a question on the exam, what it'll probably look like is something more like this. There'll be a surface given as an equation, and the question will just ask, what's the partial of one variable with respect to the other variable? And it's part of your job to remember that there's two parts to this question. First, you have to establish whether or not this thing that we're taking a partial derivative of is even a function in the first place. That is, it's not explicitly directed in the question, but mathematically speaking, it has to be done to establish that the question even makes sense. And you can't just assume, Bray wouldn't ask us a question unless it made sense. You sure about that? Right? I could absolutely ask a question, the answer to which is, what is the partial derivative? Well, that thing is not a function, so this partial derivative you have requested is garbage. That would be a perfectly reasonable question to ask. Right? So don't assume that the thing that I've asked you to compute is not garbage just because I typed it. Does that make sense? There's also, by the way, the legitimate possibility of error on my part, right? So again, don't trust me. And furthermore, when you encounter these kinds of questions outside of Math219, don't assume that the person who's asking you the question has already confirmed, right? There's all sorts of reasons why you should not assume that this is not a garbage question, right? So when you see one of these questions on the exam, checking whether the thing that you want to view as a function actually is a function is a huge part of the solution. Typically, when I grade these questions, typically it's about half. Right, so half of the points on the question would come from this, and the other half of the points, ballpark, would come from this. So, heads up. Make sure you treat these kinds of questions appropriately. Okay, and we're done with chapter 2. And we move on now to chapter 3. So now, of course, we've already done section 3.1. That was a tool for allowing me to treat the chain rule the way that I like to. So we've got that behind us. 3.2 I'm going to be pretty quick with. It is, there's some material here at the very beginning that's very important. We're going to talk about this thoroughly. And then there is an easy calculation, and then followed by an example sort of application that we're just not going to have much use for, so I'm not going to spend much time on it. And also, it's very pluggy-chuggy, and so there's really not much to worry about. So here we go. Suppose I have a parametric curve, like so. And I'm interested in computing the length of the parametric curve, and broadly speaking, sort of the big strategy for computing the total length, let's say, for example, of a curve like that, is to chop it up into little pieces, and then to try to understand on each little piece that I'm going to call ds, compute what that ds is, and then we're just going to add up those little lengths over the entire curve. I mean, big picture strategy, that's what we're going to do. So before we get ahead of ourselves, though, we need to start off with, I need to understand how would I describe the length of a piece of parametric curve. And the first object related to this to consider is what I'm going to call the dx vector. And keep in mind that x is a function of t. Let me get rid of that green here momentarily. The dx vector means x is a function of t, and dx is my linear estimate of how much that position x changes. So I was here. I over this little piece of curve moved to there, which is an increment, an actual change in the position that I estimate by way of the differential, which of course is just done with the derivative. And so easy formula to write down for what dx is. It's a displacement, and displacement is velocity times time. Old fact of physics, which is said differently. Just, of course, keep in mind we already know that x prime is the velocity, so these are really the same equation. All right. So if we've got that dx vector, in the limit, we expect the length of the piece of curve to be pretty much the magnitude of that dx vector. So that gives us these formulas down here. Everybody good so far? Right. Okay, now related object. This, what we're going to call unit tangent vector, capital T. And the book uses the same notation I do, and I'm almost exclusively going forward going to use capital T vector as a standard notation to represent this unit tangent vector. So it's tangent to the curve in the direction that the curve is going, tangent at the point that I'm interested in. So we'll be using that a lot. And of course, notice it points in the same direction that the velocity does. So if it points in the same direction as the velocity, let's see, the velocity may be something like that. That's the velocity. Then, okay, well, velocity divided by the magnitude of it's the unit vector pointing in the direction of this velocity vector that I already have. And we unitize or normalize a vector by dividing by its own magnitude. All right, everybody's happy with that? So the reason this relates to this previous calculation is, let's see here, that if you think about this formula for t, and if you think about this formula for ds, multiplying t times ds means I'm multiplying this times that, and notice magnitude of v cancels, and we get exactly v dt, otherwise known as the dx vector. So just kind of a neat little observation. This is an alternative way to write the dx vector, and there's going to be moments when this is going to be very useful. Sometimes it's going to be super convenient to write dx as x prime dt, but there will be other times when it'll be super convenient, in fact, kind of critical, to write it as t ds. So, okay. Now it's kind of all over but the shouting. We've got a formula, let's see here, for this ds vector. ds vector is v dt. That's what this little bitty length is that I'm going to then be adding up over the entire curve. Therefore, that's what I'm taking an integral of and plug and chug to compute. Is everybody with me? All right. Yep.
How can you take an integral of that if it's not a function?
If
It satisfies the vertical line test.
Right, because I'm not taking an integral of the thing representing height here. The vertical axis is not. This is not a graph. And notice also, I'm not computing area under a curve, right? So what you're kind of implicitly making a reference to there is an old, useful, single variable calculus fact that if you're interested in computing the area, which we're not, under a graph, which we don't have, right? Then yeah, absolutely, right? But we're doing something totally different from integrals, from that with this integral. This is just an integral where we're adding up a bunch of stuff. Think of this as a Riemann sum, not as a sort of area under the curve kind of a thing. Is that cool? Yeah. Cool. All right. So here's an example. Y'all can work through the example. It's pretty straight up. We have a position vector describing our parametric curve. We take its velocity here. The magnitude of the velocity is that formula. That magnitude ends up being a square root, and so altogether then when I compute the integral of this, well, okay, I'm going to have a super annoying single variable integral to have to compute, and very often this is how these questions turn out. The integral ends up being ugly because magnitudes are unavoidably square roots. Square roots are not exactly consistently, very commonly ugly integrals, right? So this is just the nature of the beast. Okay, and by the way, just real quick, I am not a monster, and so on an exam, right? If I ask you to compute a length of a curve, and if you apply the formula, if it's something that ends up like this, then I would phrase the question as represent the answer as an integral, but don't compute the integral. Something like that. If I don't represent it like that, then that means that I've already worked out the integral, and the integral's not bad. And so if you find yourself seemingly having to compute an integral that looks monstrous, something's gone wrong. That's just a strategic observation. Okay. I'm going to go really fast through the rest of this because it's mostly computational. The applications of the idea here are pretty thin, right? Most of the applications to this arc length parameterization business are for proving formulas in an area of discussion that this course just is not going to go into. So I don't think this is, again, I have to make all these tough choices as to how to spend class time and what to make you all worry about and what not to require you to worry about. So I'm going to hit certain highlights here, and then we're going to move along. So first observation I want to make is just a reminder, curves have more than one parameterization. They have lots of parameterizations. So for example, here's an easy parameterization. This is a parameterization of that curve. In fact, this is what we've previously called the graph parameterization of that curve. Make sure you're fresh on this idea. The graph parameterization is very, very useful. Okay? So make sure you're good to go with that. But now check it out. I could just say, hey, how about this? I'm gonna let t be q cubed plus q. I pulled that out of basically thin air. And if I just plug that in, here, then what I get is a completely different formula. Totally different parameterization. But nevertheless, still a perfectly valid parameterization of the exact same curve. Right? So this observation in mind, you can imagine, well, there's just endless different parameterizations for the same curve. So the big idea of an arc length parameterization is to work out the way to use arc length itself as the parameter. In other words, don't think of your position as a function of time. Think of your position as a function of distance traveled. And here's the real world analogy that I like to think of, and that is mile markers on the highway. I don't know if y'all have ever noticed. As you're driving down the highway, there'll be these little bitty signs that are, sort of tall and thin, or at least the ones I've seen, tall and thin, and it'll say 175 or whatever. And what that means is that point where that fence, where that sign is put into the ground, that point is 175 miles away from some fixed reference point. Right? So, for example, if your fixed reference point is here, and you start driving along the road, let's try to keep it on the road, driving along the road here. After you've gone a certain amount of time, who cares what the time is, but once you've traveled a certain amount of distance, then you can talk about your position, x, as a function of how much distance have you traveled, s. In other words, where are the mile markers, roughly speaking. So why this is useful is for sort of mathematical, proofy, rigorous kind of reasons involving proofs that we're not going to do, which are also just beyond what this course is really about. So it's pretty hard to motivate the reasoning. Here's an example of how such a calculation goes down, and I want to point out also, even in a really good case, these calculations are extremely inconvenient. They're rarely actually going to buy you anything, even when they're relatively tractable. So I went to some trouble here to find a parameterization such that when you compute the velocity, you compute your x prime, and compute the magnitude. Of course, the magnitude is the square root of the sum of the squares. That square root ends up being, look what I did here, it worked out to being that we're taking the square root of a perfect square. That was a trick shot, right? This does not happen as a rule. And so we managed to beat the odds and come up with an integral that I can actually do, and I'm still in trouble because in the process of trying to solve for t, now, even though again I worked the trick shot so that the integral is doable, it's still hard to solve for t because it's a cubic equation. So it's a weird process and fraught in most cases. So I don't want to spend a lot of time talking about it. Is everybody comfortable with that? Okay, so we're going to move on and get to some truly new and important stuff that will figure dramatically into what we're going to do over the rest of the course, mostly later, to be fair. But a very important idea that's going to be huge in the rest of the course and huge in several engineering and physics courses that many of y'all are going to be taking in the future. And I want to introduce the idea of a vector field. So here we go. A vector field is, you think of this picture as the short version. So to be fair, to be rigorous about it, a vector field is a function such that at any given point in your domain, Rn, such as let's say this point here in R2, for any given point, this vector field function gives you a vector in the exact same vector space. So also in Rn, but which we are going to view as being a vector and not as being a point. Now that is a weird sort of aspect of this, right? So what goes in as a point, what comes out as a vector. Of course, there is this canonical isomorphism, and we tend to blur the lines between point and vector in a lot of circumstances, but it then falls to us to always be careful to interpret appropriately to the context. And in this context, the input should be thought of as a location, and the output should be thought of as a direction and a magnitude, namely as a vector. So point is the input, vector is the output. And then notice that gives us this picture here, because for every point we get a corresponding vector that we draw with its tail at that point. That's a convention. And this point over here, fine, we get a vector at that location, different vector, of course. And etc. At every point, there is a usually different corresponding vector. And that generates this kind of picture that we started off by kind of waving our hands at, that it's a bunch of arrows seemingly indicating a sort of a kind of a, if you will, kind of a flow of something. Everybody on board? Three-dimensional version. Harder to draw because we have two-dimensional paper, two-dimensional screens, etc. But again, in 3 dimensions, for every point, we can talk about what is the corresponding vector at that point. All right, now, first observation I want to make, this picture here is not a graph. It's not a level set. It's not a parameterization. It's not what I like to call literal picture, domain and target being written separately and, with an arrow in between. We had four previous ways of drawing pictures to represent a function in some sense. We had 4. This is none of them. This is number 5. Right? So, it's just characteristic of multivariable calculus that we can't view every picture as being a graph. We just can't. They're really, really importantly different kinds of pictures. So yet another one here. All right. Okay, so a couple of examples. This is just to get us comfortable with all of this. So here's a function representing a vector field, and notice at every point for this particular vector field, every point has the exact same field vector, 2, 1. So I get the exact same vector. Oh, come on. Exact same vector. Same direction, same magnitude at every point in the domain. So that gives me a vector field that looks like this. This is, now again, that's a kind of a different than you might have expected. A lot of people are accustomed, if you have a function that's a constant, shouldn't the picture be like a horizontal something, a line or a horizontal plane or something like that? Because you're accustomed to thinking of graphs. This is not a graph, right? So this is a constant, but all the arrows point, in whatever direction of the vector that is that constant. Everybody happy? All right. Okay, here's another one. This is a little bit of a weird one. For every point, x, y, okay, weird. The field vector. Now, the first thing I'm going to notice about this field vector, also x, y. But now keep in mind, the field vector has to be interpreted as a vector. So even though the input is x, y, that's viewed as a point, the field vector is the vector that is the position vector for that point. Right? This right here is what the vector x, y looks like given that green is the point x comma y. And then reminder, the convention when you're drawing a vector field, the convention is to draw the arrow such that the tail is at the point. And so we draw it over here like this. Everybody good? Okay. So now this is a picture of, an in and an out for this vector field, but that's just for one particular point. You can do the same thing at a bunch of different points, and all together then you're going to get a picture that looks something kind of like this, because whichever point you might be happening to look at, let's say here, for any point, the field vector is the position vector for that point, but drawn with its tail at the point in question, and so stuff like that. So you get this kind of radially outward looking vector field like so. Everybody buy it? Okay, here's a fun one. For every point x comma y, for example, there. What can I say about the field vector here? Well, it's not the same, right? But I will point out it's very easy to observe that the dot product here is 0. That's just, you might not have noticed that off the top of your head, but now that I say so, easy to compute that dot product. It's clearly 0. That means that these two vectors, the position vector for the point xy and the field vector negative y comma x, those two vectors are orthogonal. And as long as we're not at the origin, they are perpendicular. And they furthermore have the same magnitude. Both of these, viewed as vectors, have the exact same magnitude, square root of x squared plus y squared. So, same magnitude, but perpendicular. And not hard to persuade yourself, that what it is, in fact, is this field vector is just a 90-degree turn from the position vector. Everybody buy it? Okay. All right. Quick reminder, rotations. Math218. Make sure that you remember all of that stuff. Now let me just remind you, I know it's been a while since you did 218. So the point is, a rotation is a linear transformation. All linear transformations are matrices. A matrix is understood by its columns, and the columns are the images of the standard basis vectors. So you take those 4 facts that I just described, kind of put them together as applied to this claim that we're looking at a quarter turn counterclockwise, and you can straight up write down the matrix that does this. And that matrix times xy will give you exactly that. And so this is a good exercise. I think everybody should take a whack at it. Let me write this down just a little bit. What I am saying here is that this negative y comma x is equal to a particular matrix A times xy. Said differently, for a given input point, xy, the field vector is a counterclockwise quarter turn of the original position vector. So make sure you can compute that matrix A and confirm that it is the thing that makes this formula come out. Okay. If you get stuck, if you have any trouble, remember, oh gosh, how did that work again? Come to office hours. I would be very, very happy to help you, straighten out how that works. But I do need everyone to be comfortably solid, proficient with how to write down a rotation matrix, such as we see in this example. Okay. All right. So here's a real-world example of a vector field. So I'm going to write it down first with this formula right there, which is compact, but not really as convenient as this variation This is tends to be how we tend to think about it in practice, because in this form right here, you can see why I want to call it a radial inverse square vector field. So let's take this one little bit at a time. What I mean by radial is that all the field vectors point along these lines, you might say radial lines coming out of the origin. And how do I know that all these field vectors, in fact, do point in that way? Well, but notice that what we have here is a multiple of let me do it like this. A multiple of the position vector x, which of course is always pointing directly away from the origin. Right? So if you're looking at scalar multiples of something that points always directly away from the origin, then what you have is what we call radial. Is that cool? The word radial actually does mean slightly more than this as well. It's not just that the field vectors point directly away from the origin. It's also that if you look at let's see, I'll do it like this. If you look at a couple of points that are equal distant from the origin, then I need for these field vector magnitudes all to be the same. That's the other aspect of what we mean by radial. And so I need the magnitude to be strictly a function of distance. And again, you can see that that's the case here. The magnitude here, I'll do it like this. This magnitude is strictly a function of distance from the origin. Okay, so radial. Inverse square, you can see right here in the equation, inverse square, the magnitude, the way the magnitude is a function of distance from the origin is literally an inverse square relationship to distance. So you may recognize this term, inverse square, flashbacks to high school physics and talking about the gravity formula. And in fact, what we have here is literally a form that describes gravitational fields. Y'all have heard of, like a planet has a gravitational field, the sun has a gravitational field. It's the vector field representing what we loosely call the gravitational force, acting, depending on where you are. Of course, the gravity pulls in different directions, right? The closer you are to the planet, the more gravitational force there is, right? So this is an example of a gravitational field. Side note, and you may have seen this previously as well, but electric forces. Are y'all aware of how electric forces work? If you haven't had a physics course yet, it's no big deal. But in the same way that when you have two masses, there is a gravitational force attracting them toward each other, right? In the same way, when you have two charged particles, there is a force either attracting or repelling those two particles. Again, inverse square on distance, and directly along the line between them. And so electric fields, other than some constants and different physical interpretations, electric fields look just like gravitational fields. They're both radial inverse square. In other words, they both have this form. So this is one of our first interpretations. Well, let's say it differently. This is one of our first applications of a vector field. Why are we interested in pictures like this and formulas that give pictures like this? And it's because this is what physical forces very often look like. Gravitational forces, depending on where you are, there's a certain vector. Given a location, there's a corresponding force. So given a point, there is a corresponding vector. It's literally exactly a vector field. So one of our first big applications, uses of vector fields, they represent forces. It's pretty useful. Okay. Now here's another, just a kind of an example, you'd be surprised. This example is actually more important than it looks. Why it is more important than it looks, I'm not going to be able to reveal until chapter 6. So it's going to be a ways off before we'll actually pull back the curtain on that. But I claim these are very, very important vector fields. So anyway, here it is, just the observation. If you have a function, let's say, for example, this one, you can talk about the gradient of that function and check it out. What this gradient is for any given point, xy, this formula gives you a corresponding vector. That's a vector field. We never thought of it in that way before, right? We've been doing all sorts of stuff with gradient. But we've been focused on sort of one little bit at a time, namely, given a specific point, that's all I'm interested in is the one specific point, and at that one specific point, the gradient is just a vector, full stop. At that point, it's just a vector. I'm just making the observation here that you don't need to restrict your attention to just a single point. I can be interested in this idea that at any point, wherever I might happen to be, there is a corresponding vector. And that is just straight up what that is. All gradients are vector fields. So, innocent observation. And again, turns out they're really important and really, really not obvious why these are such important vector fields, but they are, and that's all I'll say about that. Quick reminder, if you draw the graph of a function, let me get back into highlighter mode. If you draw the graph of a function, the gradient will always point uphill. And notice that happened here, right? So the graph is kind of a bowl. Well, it's a paraboloid, sort of a right side up serial bowl, as it were. And notice the vector field, the gradient field is always outward. And if you think about it, that's how a bowl works, right? Uphill. If you're inside the bowl trying to climb up, you're always moving away from the z-axis. Okay, so innocent observation, just a reinterpretation of old news. All right, now let's talk about terminology. I'm going to start with what I consider to be the most reasonable terminology, and then after that, we'll talk about what is actually most in circulation. They're not the same. Suppose you have some function, and you compute the gradient, which gives you a vector field, as we just discussed, right? Well, the vector field we refer to, because I computed it as being a gradient, it is the gradient of the original function. Whatever the original function was, I'll do it like this. Whatever the original function was, the vector field is the gradient of that function. Well, likewise, I think the original function should be called the antigradient of the vector field. Now, I'm stealing shamelessly here from single variable calculus. And think back to in single variable calculus, we talked about derivatives. I said we. Y'all in your single variable classes talked about derivatives, and then somebody brought up the idea of an antiderivative. That's just, it's where the derivative came from. It's going backwards, if you will. It's undoing the derivative. There's lots of different ways to kind of say it. So I'm ripping off the same idea here. The gradient of a function is a vector field. The antigradient of a vector field would be that function. So I think this is extremely reasonable. Again, total rip-off of a grammatical model created with derivative antiderivative in Calc 1. So what could be more natural here? Okay, now what are you going to hear most often, especially in like engineering and physics classes? Sadly, unfortunately, from my point of view, you won't hear the term antigradient very often. I think that's weird. They like to use the word potential function, right? So why? What is that? Where does that come from? And well, it comes from a fact of physics, and that is that when you have a force, very often, if certain conditions are satisfied, and there's some delicate issues here, and I don't want to get bogged down in formalities, but very often forces can be viewed as gradients of what we call a potential energy function. And so y'all probably aware of potential energy, and if you have, like, near the surface of the earth, if we just, in this room, for example, altitude pretty much tells you potential energy. The higher the altitude, the more potential energy it has, and stuff like that. Well, if you take the potential energy function and you compute its gradient, that's going to be strongly related to the gravitational force. And if you think about gravitational force in this room, it's straight down. Here's the problem. The gradient of the potential energy function is actually straight up. Right? If your potential energy is Z, the gradient is 001. So it's up, not down. So I point out that because of this minus sign, it's not potential energy, it's the negative of potential energy. And so arguably the word potential function is kind of the exact opposite of what it is, right? It's literally the negative of the potential energy. So I've never liked this term, partly for this reason. But also partly because of the fact that we're not always doing physics. Our vector fields are not always forces. And if your vector field isn't a force, this doesn't make any sense at all. If your vector field is just some random vector field, or maybe it's a vector field that represents something else in physics, potential energy is not involved. And so the term potential function, again, I think it's got its narrow reasonableness, and I'm just not a fan. So be aware, this terminology is out there. What I like to call the anti-gradient, you're going to hear potential function. And just, okay, all right, fine. And I don't judge, right? If you like potential function better, cool, whatever. I just have a strong preference for anti-gradient. So you're going to hear me say anti-gradient throughout this course. The book, by the way, will be using the term potential function. So just keep that in mind. All right. Okay. Now let's talk about a different physical metaphor for vector fields. Our first physical metaphor for a vector field, forces, right? Vector fields are an abstract mathematical construction. Vector fields are, pictures like this. When I say a physical metaphor, what I mean is, what is it in the real world that looks like this? And forces, gravitational forces, electric forces, they look a lot like this in some form or another. And so forces are a wonderful physical metaphor for a vector field. Well, here's another one. Fluid flows. And if you think about it, if you have a fluid, let's take the fluid in this room, namely the air. The air is not stationary. I hear the AC running. So air is blowing into this room from wherever that outlet is. And then, of course, I'm probably blowing air that way, right? And so there may be, the air in this room might be kind of circulating like this, or maybe it's circulating kind of like that, or whatever. Who knows? Maybe it's this way, hard to tell, right? Maybe over there it's circulating like that, and over here it's circulating like that. Who knows, right? But any given point in this room, you can talk about what is the velocity of the air at that point. And so every location, you have a vector. That's a vector field. Let me pause on that. Were you okay with that? Or okay, yeah, cool, good. Is everybody good? Okay. So fluid flows, another wonderful physical metaphor. There's lots of kinds of fluids. Some of these look a little bit weird. You don't normally think of animal migrations as being fluid flow. We don't normally think of animals as being a fluid. But I will point out, for your consideration, water is definitely a fluid. But water is made up of a finite number of particles. I'm going to call them particles, right? They're molecules, right? But it's little itty bitty teeny weeny little things that are kind of moving together. That's what animals do, right? If you have a mass migration of wildebeests or what have you, right? And you've seen these amazing photography things that they have these days, and there's bazillions all moving together, and they're not necessarily all moving exactly with the same velocity, but like they're kind of all, there's this kind of consistency. Over here, the ones that are all right next to each other over here, they're all kind of moving with their velocity, and then over here, maybe they're moving with a slightly different velocity, but again, kind of like a fluid, they're all kind of flowing together. It's a fluid flow. It's a weird fluid flow, but nevertheless. Okay. All right. So, there's a calculation I want to do now that involves interpreting vector fields as representing the flow of a fluid, and there's a specific physical idea that when you have the flow of a fluid that you'd naturally be interested in. So here's the physical idea. Now again, starting with the assumption that my vector field represents the velocity of the fluid at any given point. And here's the reasonable question. If I have a surface, and if the fluid is flowing, keep in mind the vector field represents the velocity of the fluid as it flows. Reasonable question, how much volume of fluid per unit time is passing through that surface? Right? I mean, so one example would be, to say you have a water hose, right? Well, there's fluid flowing through your water hose. And you can talk about the velocity of the water in the hose. Sure, that's one relevant object, right? But how many gallons per minute are flowing through that hose is a different question. That make sense? And so what's the relationship between them? So here's another example that I like, not that different from a water hose if you think about it, but a river. You can talk about how fast the water is flowing in the river, but another really interesting question, but how many gallons per second of fluid are flowing into the ocean at the mouth of the river, right? Does everybody know what I'm talking about there? By the way, I'm going to say, I think an underappreciated point of view on rivers, and y'all may have learned when y'all were in elementary school or middle, whatever, they talk about this, like, longest rivers in the world and all this kind of stuff. And it occurred to me recently that while that is, I suppose, an interesting feature of a river is how long it is, also really interesting, if you want to talk big in connection to rivers, I propose gallons per second that flow into the ocean. And so I don't know if y'all know the numbers on the various rivers. So there's like 4 or 5 rivers in the world that are all they're all preposterously long. I forget what it is, several thousand miles long rivers, right? And the Amazon River is one of them. Neck and neck, they're within 10% of the same length of each other. The Amazon's flow rate, gallons per minute flowing to the ocean, is like 5 times bigger than the second biggest river. There is only one big river in this world. Length is not the point. It's just the sheer mass of volume of water flowing into the ocean. It's preposterous. The Amazon's I literally think it's a factor of 5. It might be a factor of 7. I don't remember. It's way up there, not even close. I don't know. I just thought that was an interesting sidebar. Okay, so let's do this calculation. I'm going to compute first in a given amount of time. I'm going to compute the actual volume. Here's the little parallelepiped representing the actual water, delta V, that has passed through in some given amount of time, delta T. And let's compute what that volume is. It's no big deal. The volume is what I'm going to call the height here, times the area of the base. Right? Flashbacks to high school. Height times the area of the base gives you volume. Yeah, everybody good? Alrighty, so let's compute that height. I propose, and I should label the, I've kind of glossed over the H there. Let me make that more clear. So that height, I'll observe, is a component. It's the component of what I'm going to call the displacement vector, which I drew over here just for kind of visual convenience, but you can think of it as being over here or over here. It doesn't matter. It's all the same vector. The displacement vector, specifically I want to know its component in the direction perpendicular to the surface. And so I'm going to understand the way my surface is oriented by describing this, we'll call the unit normal, little n there. And so with that unit normal vector n being defined like that, and given that the displacement vector is that, then the purple component, the purple height, is just the n component of the displacement vector. Everybody see the geometry of that? It's just a little flashback to chapter 1 there. And of course, I compute components with dot products, specifically because the normal vector is a unit vector, and components or dot products with a unit vector is one of our memory tools from chapter 1. So we're basically done at this point, except to understand how this d vector is computed. And keep in mind, it's how much the water is displaced. Any particle of water is displaced. And displacement is velocity times time. And of course, the vector field is the velocity. This is our sort of first assumption about the vector field. That vector field is velocity. So velocity times time gives you displacement. And we're basically done with this calculation now. Now, before I clean up my highlighting, does everybody follow me down to this part so far? Everybody's good? Okay, now I'm going to erase all this so that I can work without the mess. And keep in mind what we were interested in. What we were interested in is flow rate, volume per unit time. I've just computed volume, and I see that it is a multiple of time. So volume per unit time, then, is just what we have on the right-hand side here, F dot N times the area. And it turns out this is a really important calculation, relating a velocity of a fluid to a flow rate of a fluid through a surface. So this expression, F dot N times area, is going to come up a lot. It's sufficiently often comes up that we have a name for it. We call it flux. It's just a word, but it means this expression right here, F dot N times area. And we have a standard notation, which is a capital Greek letter phi. And I emphasize it needs to be capital because the lowercase phi, of course, is spherical coordinates, and we don't want to use the same thing for two different things. That's if we can possibly avoid it. So capital phi, and thus it needs the little bars on the top and bottom. Yeah, Green Lantern-esque. Okay, is everybody happy? All right. Now the related calculation that I want y'all to do for yourselves is going to be pretty much a rip-off of what we did here. Almost exactly the same thing, but with a different sort of assumption and a different sort of question, but nevertheless very closely related. Sometimes you don't represent fluid flows by velocity. Sometimes you represent fluid flows by density, weirdly, times velocity. Why would you do that? Seems weird. And the reason why broad brushstroke is because if you think about let's think about a bunch of birds flying around. And of course, birds are a fluid of sorts, right? And if I know the birds are flying really fast, and I've got a big rectangular frame for whatever reason, I'm interested in how many birds are flying through my big rectangular frame, right? How fast they're flying is part of the story. But if there's only a very sparse collection of birds, the fact that they're flying fast doesn't mean I'm getting a lot of bird flow, right? If there's a dense, there's just tons and tons of birds and they're all, very compactly, densely packed together, flying the same velocity, now I've got tremendous bird flow. Does that make sense? Silly metaphor. So the density kind of matters, right? If what you're interested in is quantity per unit time, not volume per unit time, density ought to be in there. And so the calculation I want you all to do, and it's going to be, again, a very similar to what we did here. Very, very, very similar. Show that if you compute quantity per unit time, I'm calling it here mass, just as for example. But if you want to compute quantity per unit time, not volume per unit time, then again, you get F dot N times area. Namely, again, flux, same symbol. Right? So these are two different interpretations of flux. If you are talking about this kind of a vector field, flux gives you quantity per unit time. And if you are talking about this kind of vector field, then you get volume per unit time. So do this blue calculation. Again, it's a shameless rip-off of the green one. And if you have any trouble, come on into office hours. I'll happily help you out. See y'all later. Sorry to go a minute over. I lost track of time there.
Wait, so what are the units of that?
We don't want to. That's somebody else's problem. Don't worry about it in this context. It's a lot to keep track of.
What do you call this symbol?
What do I call what now?
What do you call the symbol, the curly D?
This right here?
Yeah.
Oh, that's just that's the Greek letter delta, and we typically use that to represent density. So it depends on what kind of a fluid you're talking about. If you're talking about birds, then it's number of birds per unit volume. If you're talking about mass, then it's mass per unit volume. So it kind of it just depends on the context.
So delta V is velocity per unit volume.
So what now?
I got it was density, but density of what?
Density of the fluid. So whatever your fluid is. So if you're thinking about air, how air is flowing around, well then you need if you wanted to do this blue calculation here, you'd need to know in a given amount of volume how much mass of air is there in that given amount of volume.
So what does that have to do with velocity?
It doesn't. It's a different consideration. So velocity is one thing that a fluid can do, right? But unrelated to the velocity of the fluid is the density of the fluid. So air has a certain amount of mass per unit volume, right? Whatever that density is doesn't directly pertain to how fast that air is moving. Does that make sense?
So the symbol is just to notate that it's...
Yeah. So I'm representing that my vector field here represents a product. My vector field represents mass per unit volume times the velocity of the fluid that's moving. And this is just, this is how you have to understand a vector field to represent a fluid if what you're interested in, if, the thing that you want to compute is mass per unit time.
Okay.
Yeah.
Okay.
Cool. All right.